Okay, good evening. Right, so today we are going to do some past paper questions on databases. Just give me 1 minute. Okay, so we did plenty of past paper questions on transactions. So therefore, we are not going to do anything on that unless you have any specific questions. So yesterday we discussed about, the day before, right? We discussed about the stored procedures and triggers past paper questions as well. And if you have any specific questions, if you ask, I can explain. So what we need to do is do a little bit on query optimization, indexes, past papers. Okay, the topics are done. So you can always refer to your recordings. So therefore, I'm not going to do the things again because that is waste of time when you have the recordings with you. Rather, we are going to do past paper question, assuming that you have studied the topic and you know what are the indexes, calculations, you know how to do the query optimization, things like that. Yeah, fourth session, yes, I know. Fourth session is the distributed databases that we will be doing because distributed database also ultimately connect to the query optimization. Okay, right. So yeah, so thank you. That actually I forgot to mention about that. We'll do that after doing some questions on these topics because ultimately distributed database questions may also be connected to query optimization. Okay. Right, so straight away, let's do some past paper questions. And this is where the questions are extremely difficult. Of course, transaction management, once you understand, it's easy. If you haven't understood, transaction is the most difficult. But these questions, even though you try to understand, examiner will somehow come up with a fuzzy question, and also the huge area is there. Okay, right, so let's look at the past paper questions. So let's look at 2020 paper. I'm specifically interested in this. Okay, so theory questions are not that difficult, right? So briefly describe the following 3 index types: primary index, secondary index, clustering index. Now you must have a very clear idea about these concepts. Remember, we can subdivide indexes or indices or whatever into 2 categories. One is primary index and secondary index. Okay, so secondary way of connecting. Okay, so that is primary index. That is your actually we can subdivide it into primary index, clustering index, and secondary. Yeah. So primary index is your index field is the primary key. So then you just have the index file for the primary key and the block pointer, and that's it. Then you have the clustering index. So actually this is how you subdivide primary index or clustering index. Clustering index means your physical file, your data file is sorted by a different field rather than the primary key. So then we call it clustering index. So you can't have both primary index and clustering index. Just either you can have primary index or clustering index. So then you can have secondary index. So that is a second different thing. Secondary index. So secondary index means you have secondary file. So here you have your master file. If it is primary index sorted by primary key, and you have an index file. So it has the primary key and block pointer. Okay. If it is a primary index, if it is clustering index, this is sorted by non-key field, maybe something like email address, whereas the primary keys may be the employee ID or maybe department ID, right? So physically it is sorted by that clustering field. And again, you have a file which has the clustering field and the block pointer. Okay, so So initially you look at this and you go to the block point and you go there and find the record. So therefore, obviously the physical data file can be sorted either by primary key or any other field. That means primary index or clustering index. So therefore you can have only one of those, not both. So the secondary index is different. So now your secondary index is while your primary, actually that is little bit confusing, because actually when you say, sometimes you may feel like secondary index means when you have primary index, the other index. No, when you have primary or clustering index, right? So you have primary or clustering index, then you can have secondary index, right? So now that means you have the primary index or the clustering index, and you can have another file, index file, where you have another field and block pointer, right? So the biggest difference is whether it's primary or clustering, this is sorted by that field. If it is primary index, sorted by primary key field. If it is clustering index, it is master file is sorted by that clustering field. Okay. But when it comes secondary index, now already your data file or master file is sorted by primary key or the clustering field. So therefore, so this one is referring to a file, but that file is not ordered by your secondary field, secondary index field. Maybe it has a primary index, therefore it's ordered by employee ID. Now your secondary index may be by a department ID or by email address. Obviously, this is not sorted by email address. Okay, so hope you can understand it. Okay, so then there's another categorization of indexes, that is single level, multi-level, right? Single level index, multi-level index. So single level index means you have just one index file. Multi-level means this index file, from the first index file, you go to the next index and maybe another index set of index files, and then only you go to your data file. So that is called multi-level index files. So why multi-level index files are used? If you have so many index entries, especially it can be helpful for secondary index. Right now you should know why I'm saying, when I say it is more useful for the secondary index, you must know why it is more useful for the secondary index. Can someone tell me why it is more useful for the secondary index, these multi-level indexes? Anyone? So now you have to reverse thinking. So multi-level indexes are more useful when you have a lot of entries, right? A lot of entries. So then only it is going to be benefited. And where are we going to get a lot of entries? Because secondary indexes, a secondary index is not sorted by, or your data file is not sorted by secondary field. So therefore, for each record entry in the data file, there will be entry in the index file. So therefore 1 million record here means in the secondary index file also 1 million record. So you can see that. So these secondary index files are huge in the number of records. So when the number of records are high, we can break it into hierarchy and create because that is going to make it a lesser number of access. Okay, right. And especially when it comes to clustering indexes, you have to think whether that clustering field is unique field or non-unique field. Now remember, secondary index is always dense index. Dense index means if you have million records, your index file has million record. But here, primary key index is typically sparse index. That again, you must know why. So when I say something, if you have studied it properly, now you must be able to tell why. And clustering indexes can be sparse or dense, right? If the field is unique field, then we have a better chance of making it a clustering, the sparse index. But if it is not a unique field, like that's something it can be repeated. Of course, it can also result in sort of a dense index. Okay. Right, now let's look at the answers. Primary index. So primary index is the primary way of accessing the your data file, and typically the primary index is based on your primary key, and the primary index will have the primary key and the block point of the relevant block for that particular record. Okay, particular record. Right. So that is how you do it. That is how you are supposed to explain it. Okay. Secondary index is secondary way of accessing where you have your data file is not sorted according to the secondary index. A secondary index is a secondary data index file. First you access that and then you go there. Here also primary index also first you access your primary index file, then you go there. Okay. But only thing is this is physically sorted by that. Okay. Let's see and clustering index is pretty much like primary index, but the index field is not the key field. Right. Primary index is defined on the ordered data file. Obviously, it is ordered data file. The data file is ordered on key field. So we have to say that yes, it's based on the ordered data file, and it is if it is ordered by the key field, we call it primary index. The key is generally the primary key of the relation, obviously, right? Right. So any questions on that? Because first of all, you must be really sure about your concepts. Right? Really sure about your concept. Otherwise, you will be totally lost. Right. Secondary index. Secondary index means it's a secondary way of accessing your file. While you have the primary or clustering index, you can have secondary index, and the secondary index is based on a secondary field, but the data file may not will not be sorted by that secondary field. So therefore, secondary index is definitely invariably a dense index. Okay, so let's see. Secondary index may be generated from a field which is a candidate key and has a unique value in every record, or non-key with duplicate values. Of course, it can be either unique field or non-key field, right? So that is not a very important thing. Basically, it can be anything other than your primary or clustering index, right? The candidate key here කරලු නැත්නම් candidate එක නෙමෙයිලු. ඒ කියන්නේ ඕන එකක්. Right? මම දැන් ඇයි ඒක එහෙම කියන්න ගියේ කියලා. Right? So it can be any field other than your primary or clustering index field. Right? And so then it's a secondary way of accessing it. Other thing is the secondary index field is that your data file is not sorted by the secondary index field because it has a primary index or clustering index. Okay. Right. Third one, clustering index. It's pretty much like primary key index, but the index field is not the primary key. But your data file and your clustering index file is sorted both by the same field. Clustering index is defined on an ordered data file. The data file is ordered on a non-key field. Okay, non-key field. Your data file, it's very important. It is your data file ordered on non-key field, right? And you have the clustering index file. Always there's an index file. Okay. Either you have the primary index file or clustering index file. And while you have primary index or clustering index file, you can have any number of secondary index files. Okay, but you can have only one primary index file or clustering index file and any number of secondary index files. Okay, any number of secondary index files. Maybe we are interested in search by email address, search by salary. Okay, right. So I hope you can write, right, really good answer for that kind of a question. Right, consider the following relational schema taken from the university database. Okay. Staff, primary key is employee number, name, department, designation, date of birth, and salary. So this must be the primary key. Name, department. I hope this will be department ID, date of birth, and salary. Okay. Given below are two SQL queries executed using two different query plans. Suggest the most suitable index file organization for each query. Justify your answer. Right. So when you're answering these kind of questions, now remember we discussed about a primary index or clustering index versus a secondary index. Okay. So then you have to think about whether it is single level or multi-level, right? Maybe. And also there's a possibility of composite keys, right? More than one field is your key index, okay? And also implementation of index. Remember, there are different ways you can implement index, right? So the most obvious things are the hash index versus B+T index. And you must know the difference between hash and B+T index. Right? Because you had enough time to search. If you haven't understood it yet, if you haven't understood what I explained, right? What is the difference between hash index and B+T index? Okay. So hash index is good when you are not. We are just mostly searching. Your search will just result in a single record. Maybe email address, obviously, right? If someone search by email address, no two records are going to have the same email address. So that kind of a index, maybe clustering index, okay, or the primary index or secondary index. If it is resulting in a unique record, right, that index field, hash index is good enough. And the other thing is, we must not be searching, or we must be searching for single records, not where we are going to get entire things, most of the records, right? Something like that. Because remember, when you have the hash index, hashing is trying to randomize. Maybe the first one, Amal is here, Amila is somewhere here, Bimal is here, and Chamal is here, and maybe Vimal or something here, right? Because they try to randomize. So therefore, if you are looking for range searches, or we are going to get, say, a lot of records for a particular query, so then hash index is not the good thing. Then the B+T is better, because remember, B+T, you have a lesser depth, and also the last level is linked list. So therefore, it can go from the first that record to the next record, okay? Right. So think about all those things, and still the question can be fuzzy sometimes, right? Because it's the nature of the question, right? So sometimes what I think is not what the examiner is thinking. Maybe he thinks that something else is more important. That is something that we have to live with when we are doing this kind of question. And of course, you can't skip these questions. Okay. Now let's see. Given below are the two SQL queries executed using two different query plans. Suggest the most suitable index file organization for each query. Now, don't think too much about the rest of the thing. Just narrow it down, right? You are a very selfish person. You just want to somehow make this query faster. So that must be the sort of attitude when you are answering these kind of questions. Okay. Right, because this is for that query, right? For these queries, right? Okay, now let's see. First one, so it's a two questions. Select name, salary from staff where department is computer science or whatever, CS. Okay, so it's a staff table. is staff table, and they are going to search by salary. And salary, where is that? Yeah, sorry. They are going to search it by computer science or CS. What do you think? So this is a very open question, right? So obviously we may not be able to go for primary index, okay? Because you have to give a query plan. How are we going to do it? First, we use this index and go to the data file and blah, blah, blah. Okay. So therefore, we can't do it by the primary index, obviously, because primary key is employee number, but we are searching it by the department. And there can be only few departments, right? Typically there will be only 3-4 departments. Maybe there are hundreds of staff members. I don't see any reason why we want to get rid of primary index, because you can't have the primary index and clustering index, right? And going for a clustering index just because this query, if I want to be more reasonable, I would prefer to go for a secondary index, right, rather than a clustering index, because I feel like there will be a lot of places where they want to search by employee number. Therefore, I will go for primary index, and I will go for secondary index for department field. There's something called index only plan. I will not go for index only plan because these are there are two fields as well. Index only plan means you just refer to the index file and you don't go to the data file at all. So that means if there's just one field, you keep that field also in the index file. Okay, if it is frequently needed. But that increase the file size and the redundancy. But at the same time, it increases the efficiency. So so there can be a lot of people with this department as well. Okay, CS. So therefore, I will go for, again, it can be debatable because these are the decisions. I would say maybe hash index, right? Hash index, or even B+3 is okay for me. Okay, B+3 is okay, but I prefer to go for hash index. And it will be secondary index for me. My decision is secondary index, and I will implement it as a hash index. So that the hash value give you the block number where all the employees. No, that is also not going to work, right? Because there can be so many records, right? With CS, yeah, first you have to go there. So the index file is going to have the the department ID and the block pointer. Okay, so department ID and the block pointer. But this is going to give you a lot of records, right? When it gives you a lot of records, I don't think, because there can be so many employees with that department, right? How can we do that? And yeah, one thing is maybe you get rid of the primary index and go for clustering index. If this is extremely important, maybe that is one possible solution. Because this is not like something like email address or something like that, where we get one record, right? So the CS, say computer science, there can be so many records. Okay, I don't know. It looks like I prefer to go for then. If I think about only this one, maybe clustering index rather than the primary index. Okay. Or else, do we have any other option? No, I don't see any other option, reasonable option. I will say go for clustering index. Okay. Okay, let's see. Now these questions can be a little bit tricky and the examiner might think otherwise. Anyway, let's see. Clustering, yes, you can see that. So you can see that how much I had to argue with myself to come up with this answer. Clustering index is more suitable when records are required on a non-key field. Because this is a non-key field, multiple values are there. Actually, I first thought we can go for a secondary index. Then I found that, okay, multiple values can be there. And if it is a secondary index, your records are here and there. So how can you link it? Because there can be one students or staff member with department CS somewhere here, because his employee, maybe it's a primary key, employee number is 10. Other one is employee number 100 in a different block. Other one is employee under 150, maybe another block. How can I connect to these multiple places? Because they are here and there. If they are in one block or at least the adjacent block, I don't mind. Okay, so that is why I decided not to go for secondary index, rather decide to go for clustering index. But of course, if I go for clustering index, there won't be any primary index. Okay, right. So lucky, you need a bit of luck also. So anyway, I didn't read this paper, right? This is 2020. I'm looking at this question paper actually only now. Right? Sometimes I just have a look at the paper and do the discussion. Actually, I never got a chance to read honestly. So I'm also looking at these questions right now. Okay. Sometimes I have a look at it and come, but this one, this is the first time I'm looking at. Right. I had a little bit of luck also. I got the correct answer. Okay. Second one. Of course, you need not a little bit of luck, lot of luck to get this kind of questions right. Okay. Unfortunately. Right. Select name designation from staff where salary is greater than 10,000 and salary is less than greater than 100,000 and less than 200,000. It's a range query. So usually when it comes to range query, we prefer to go for B+3 because then those records having those salaries will be in the nearby blocks, right? Maybe 1,000, 100,000 record, 110,000, 120,000, right? So those records will be in either one block or maybe one or two nearby blocks. So therefore, usually B+3 is the physical level we need, right? And also, are we going for primary index? Obviously, I don't see it's going to be primary index because salary is not your primary key. Should we go for clustering index or secondary index? So that is another thing we have to think about. Should we go for another clustering index? Of course, you can't have two clustering index as well, but assuming these are independent questions, of course, you can say for this one, go for this clustering index, this one for this clustering index, okay? But for one table, you can't have more than one clustering index as well, just one clustering index. And also when you go for clustering index, you will lose your primary index. What are we going to do? Secondary index, is it going to work? Salary? That means your salary is your index field, right? Salary. But this query is all about salary. And again, that salary might have multiple records, right? So then what are we going to do? We have the same issue, right? Multiple records. Because usually secondary index work if it is sort of a unique field, mostly. Okay, I will go for again clustering index, assuming that these two questions are independent, and B+3 index. Clustering B+3. Yeah, the option is go for secondary, but I'm a little bit doubt how are we going to create the secondary index for this one. Okay, let's see the answer. Right, so here you can see they have given an alternative answer also. We'll have a look at it later. I told you that there can be more. Different people can look at it in different way. Okay, let's look at the second one. right? So the examiner also saying that B plus 3, right? But examiner is sort of hiding the other part of the answer. He is not saying should we go for clustering or primary or secondary. So now you can see that examiner is pretty much, right, keeping that option open, right? So B plus 3, only the physical thing only examiner has mentioned. He's silent on the logical concept, okay? B plus 3 represents sorted data and allows efficient retrieval of the records, each of which is identified by key, right? So that is obvious, right? That is why we go for B plus 3, because it is, the retrieval is faster because your next record on the sorting order of the salary will be in your index fields next record, okay? But if it is a clustering, your data file is also like that, okay? Right. It is dynamic multi-level index with maximum and minimum bounds on the number of keys each segment. In a B plus tree, all records are stored at the leaf of the tree. So you can see the examiner is only talking about the B plus tree, and examiner is really silent about whether it's a clustering or secondary, right? I hope it will be a clustering index, okay? As clustered in B plus tree index, because it's a range query. Anyway, it's a little bit fuzzy. Right. Given below are, so this is a separate question. Given below are 4 relational schema taken from same university database. So that means the same database that they talk about, that lecturers or whatever, okay, and staff members. So these are the tables: student, department, enroll, course. So that means student can enroll for many courses, course can have many students. That is why you have this connecting table. First look at it, okay? So student, course, obviously you can see student ID and course ID. That means this is the connecting table. Student enroll table. That means that one to many has been mapped, model as to one to many. And it looks like this course is where this department. Can you see anywhere that the department is connected? Course ID, course name, year, lecturer, no. Student ID, course ID, marks, no. Here you can see different department ID. So that means student will be enrolled to a department as well. And student can have only one department. Department can have, remember, many site has the foreign key, right? So department can have many students. So this is the design ER diagram. Right, now let's look at it, because otherwise you can't think about these things, okay? You don't know, otherwise you don't know how the join is happening, okay? Joins and other things are happening. And also remember, for foreign keys, typically we create index files, because join mean there's a access of the data by that field. Student file has 300,000 student records. Okay, so student file has 30,000 student records, and each record is 68 byte long. Each record is 68 byte long. The student belong to 15 different departments. So that means department table has 15 records. Right? 15 records. Okay. Department file has 15 records. Now it's saying that also, obviously, if there are 15 departments, there must be only 15 records in the department table. And each record is 30 byte long. And each record is 30 byte long. Okay. So here each record is 68 byte. Here 30 byte and there are 15 records, but here there are 30,000 records. And you have enough time for this paper, like 2 hours. Usually time will not be an issue. So therefore spend, especially do your triggers and that question first. Then because it takes less time. And possibly if it is distributed database, right? And also transaction question, if it is easy, do it. So then keep a lot of time for this one, right? Keep a lot of time, because if you try to hurry, either you will not get the answers or you will get frustrated as well. So do other topics faster and keep this usually for the last, because of the fussy nature. You need to think, right? Each student must enroll to 3 courses. So that means student can enroll to 3 courses. That means for each student, there will be 3 records here. Okay. And all that information is available in the enrollment file, obviously. Each record in the enrollment file is 35 byte. And so this enrollment file, one record is 35 byte. But this is going to have 3 times the record of the student table. Right? So the student table is going to have, they say have 30,000 records. So that means in general, assuming that each student is taking 3 courses, because it is not saying maximum, it says enroll to 3 courses. So that means this is going to have 90,000 records, right? 90,000 records. Assuming that each student is enrolled into all 3, because this is not saying maximum, it says enroll to 3 records. Assume that the block size is 1024. Right? Block size means your database or your disk can be subdivided into blocks. The block is the smallest unit that the operating system can access, and it says one block is 1024 byte or 1 kilobyte. And remember, we discussed about the block factor and other things. Right. So calculate the number of blocks required to store the file with the student enrollment details. Right? It looks simple question because no indexes, nothing, right? Calculate the number of blocks required to store the file with student enrollment details. So that is this table, right? Enrollment. And we know that each record is 35 byte. And since a student is going to enroll for 3 courses, we are going to get 90,000 records. So 90,000 records and each record is 35 byte. So therefore, what is the total size? 90,000 into 35 bytes. Right? So this much of bytes are needed. But one block is going to have only 1024 bytes. So therefore, how many blocks are needed? This divided by 1024 bytes. Okay, 1024 bytes. So that is my answer. And also you have to, if it is 2.5, 2.2, you have to say 3, because there's nothing called 2.2 blocks, right? You have to ceiling, right? You have to ceiling, not floor, not even rounding, right? So let's, I will use the calculator. Right. 90,000 into 35. If I make a mistake, just let me know. Divided by 1024. Okay, I got 3076 point blah blah blah. So that is a huge. Okay, is it possible? I don't know. What I'm getting is 3078 blocks. Can it be that big? 3078 blocks. Let's double check again. 90,000 records. One record will take 35 bytes. Right? 90,000. Is it 90,000? Yes, 30,000 into 3. And block size is 1024. Oh, yes, I got 3078. And 30,000 into 3, 90,000, correct. Blocking factor is 1024. 3,000 blocks. What I got is 3078. So this one is correct. So here examiner has taken some other path. Blocking factor for enrollment record is 1024 divided by 35. That is okay. There are one block is 1024. 1024 divided by each record is 25. Right, 35. So therefore there are 30 30 records per block. Right. Is it the exact value or rough value? 1024 divided by 35. That is a rough value, but we got it is 29.25. So they have taken it as 30. That is 30 records in one block. And we have 90,000 records. I think yes. So this should be the approach, right? This should be the approach because you can't keep half of the records in one block, right? So I think my approach has a bug. So I just multiplied 90,000 by 35 and divided by this, but that is not a good way to do. That is actually wrong. We have to take this approach, because obviously we have 90,000 records. So one block can have 1024, right? And each record is 35. Therefore, we can calculate how many records can be there in one block. Actually, this is the way to go. Though I got the roughly same answer, my approach has issue. Okay, my approach has issue. So now we know that one block can have 30. If you get 30 point something, it has to be flow. Then of course we have 90,000 records, right? And one block can have only 30. Therefore, we need 3,000 blocks, right? So that should be the answer. Okay, right. So any questions? Block factor value. So block factor is number of records per block, right? If it is something like number of records per block, if you get 2.7, right, you can't keep 0.7, right? Our assumption is, remember we discussed span and unspan. So span means it can goes to another block. Half is here, the other part is there. But usually we don't consider span. We always assume unspan. So then if you got 2.7 or maybe 12.7, your block factor, so you can't keep 12.7 records in a block. So you can just keep 12. So therefore it is not it is not sealing, it has to be flow. So your question is whether to do sealing or flooring. Yeah, we have to floor it. We have to floor it. Has the examiner floor it? I hope examiner has floor it. Let's double check. Yes, 29. Yes, so that is wrong. Yes, so your point is correct. Your point is correct. We have to floor it. So when you floor it, it has to be 29, not 30. So that is a mistake. That is a mistake by the examiner. Actually, that is a good point, right? Because you can't keep 29.25 records in a block. So it is going to be 29 records. So therefore, it should have been 29, not 30. That is a good pick actually. I also was not serious to think about that. Yes, I think, not I think, I'm pretty sure the answer should have been 29. And then you have to divide it by 29, okay? But anyway, my original approach has a bug, right? Because I just multiplied that. That should not be the case. This is the correct approach, but examiner has taken this as 30, but ideally it should have been 29 records per block, okay? Right. Right, so this is the index question and multi-level also. Now these are the headaches, okay? Right. Each index entry is 16 byte long. Right? Each index entry is 16 byte long. Say index field. Index field. Assume that it is 16 byte long. Then you have the block pointer, right? Pointer to the block. Calculate the total number of block access required to get a student record of whom belong to a given department if a secondary multi-level index. I told you that secondary indexes are really good candidate for multi-level because secondary index is dense. And now you can see its question also says secondary multi-level index, right? Secondary multi-level index on a non-key attribute department ID, right? So this must be your department ID, right? It says the index entry. But when you say index entry, I think this entire thing, right? So I hope, I'm not very sure, but it looks like index entry means the index field with plus the block pointer field, because the examiner has not given you the block pointer with. So therefore, it's safe to assume that index entry means this entire record, right? Index field plus block pointer, okay? Right. So now let's read it again. Assume that the students are evenly distributed among departments. So that is another assumption. Right. Let's read it again. If each index entry is 16 byte long, calculate the total number of block access required to get a student record of whom belong to a given department if a secondary multi-level index on non-key attribute department ID on the student file is to be used. And we know that how many department IDs are there? Yeah, has 15 records, okay? So that means there will be 15 records, right? 15 records. Actually, there will be 15 departments, right? There will be 15 departments. Okay, so now it's confusing for me also. Non-key attribute department ID on student file is to be used. Assume that the students are evenly distributed among departments. Now the index is on department ID. Okay. So each department ID is going to have multiple. Right? So altogether, how many records are there? 30,000 students. So 30,000 for one department, there will be on average 30,000 divided by how many departments they say roughly? 30,000 students, they say 15 records, right? 15 departments. So therefore, for each department, there will be 2,000 students average, because they say evenly distributed, right? For each department, there will be 20,000 records. Then how many block accesses are needed? And they say it is multi-level also. How to tackle that one? Now your index file has department ID and block pointer. And of course, if it is 30,000 students, we are going to have 30,000 entries, right? Okay, we'll think like that, right? Because there are 30,000 students, there will be 30,000 entries in the secondary field. Then the blocking factor will be number of records for block. Block size is not going to be changed, right? So the block size is 1024. Right, 1024. So therefore, let's say 1024 divided by 16 byte. I'm using the cal. (1024) divided by 16. 64 blocks are, 64 is the block factor. 64. That means there are 64 records in a block. Right? There are 64 records in a block. But we are going to have 30,000 records. Right? 30,000 records. So we have 30,000 records. And one block can have 64 records. Right? One block can have 64 records. So therefore, number of blocks is, there are 64 records in one block. Number of blocks is 30,000 divided by 64. Okay. What is that value? That is 30,000 divided by 64. 468.75 block means 469. Right? 469 blocks are needed for this one, and we have 330,000 entries. And we have to go for multi-level. Because 469 is a big number. So rather than going for 469 blocks, we can, in one flat single level block index file, we can make it less entries here because we are going to have something like this. Again, two like this. And when this is one block, we have to stop. One block kunakam make a kadaගෙන යනවා. One block kunam make කරන්න දෙන්නේ නැහැ අපෝ. අපි ඉස්සෙල්ලා මෙතන නම් ටික හරියද බලමු. නැත්නම් ඉතින් හරියට හරියන්නේ නැහැ. Block factor is 64, right? So we found that block factor is 64. Out of 5 marks, now we have got 0.5. Number of index entries is 30,000 that we also use, right? 30,000. So therefore, maybe number of blocks we need now. Right. Number of first level blocks is 30,000 divided by 64, 469. So we got that also. Okay. So that means we are on track. We are on track. Okay. So far, so good. Right. So far, so good. Now 469 is a big number of blocks. So therefore, when you have large number of blocks needed for your index file, we can go for this kind of arrangement, right? Fan out property use කරන්න ඕන දැන්. කළා එක වුණාම නවත්තන්න ඕන. ඒක ලියන විදිය මට අක්කවාට ඔලුවට එන්නේ නැහැ. හරි? But we did that. We did that in the class. Somewhere here. I used the semester 3 note. Okay, semester 3 note has a lot of information. මම ඔයගොල්ලෝ ෂෙයා කරන්න තියා note එක semester 3 note එක නැති අය ඉල්ල ගන්න මම අද ඕනනම් ආයෙ දාන්නම් ඒ ටික index okay so this one right multi level index so දැන් මෙන්න මෙතනට නිකන් ඇවිල්ලා තියෙන්නේ so you have to calculate this one fan out කර කර යන්න ඕන so we have found the blocking factor for the first level. The number of blocks required for the first level is given by R1 divided by F4. R1 කිව්වේ entries ගාන blocking factor එකෙන් බෙදන්න ඕන නේද? Number of blocks required for the first level is right. So let's do that. R1 divided by R divided by F0. Right. Number of blocks for the first level. Number of blocks is R, number of records, which is 30,000, divided by the block factor 469. So that is the first level. නෑ ඒක අපි කරලා ඉවරයි දැන් නේ ඒක කරලා ඉවරයි ඒක කරානේ sorry so second level block so this is a little bit confusing first level index has R1 entries yes number of records in the secondary level index is R1 divided by F0 මේකත් R1 divided by F0 නේ. මේ දෙකම සමාන වෙන්න බෑ. Right, maybe this is the R and this is R1, okay? Right, so number of blocks for the second level must be, so this one we have found, right, 469. So number of block for second level වෙන්න ඕන මෙයා නේද මෙයා බෙදන්න ඕන block factor එකෙන් right 469 divided by 64 බලන්න එහෙමද කරලා තියෙන කියලා එහෙම ආයෙ බෙදාගෙන යන්න ඕන එක වෙනකම් let's see whether that is the one the examiner has done yes 469 divided by 64 that is what I mentioned 469 divided by 64 so that is the second level blocks right so then 8 divided by 64 so that is the third level blocks so 8 divided by 64 when you floor it because 8 divided by 64 is a point something when you floor it you get 1 right you get 1 so when you get 1 you can stop it okay හරි first level blocks ගන්න හෙව්වට පස්සේ ඒ blocks ගන්න බෙදන්න ඕන block factor එකේ right block factor එකේ හරි ඊට පස්සේ a න ගන්න බෙදන්න ඕන block factor එකේ මොකද මේක මේ ගාන කැඩි කැඩි යනවනේ දැන් මේ මෙතනට ආවට පස්සේ මෙතන ඊළඟ එකට යන්න ඕන එතනින් ඊළඟ එකට යන්න ඕන නේ එතකොට ඔක a block factor එකෙන් බෙද බෙද තමයි යන්න වෙන්නේ so now we know that it is going to be 3 level index because we can stop it now so 3 level index means rather than you access so many blocks here you straight away found the block here then you go there and you go there ඔයාට level 3යි කියන්නේ access 3යි කරන්න ඕන right rather than accessing remember the binary search can be done rather than accessing log 2 right log 2 469 which is quite a big number now you just need 3 access 3යි කරන්න තියෙන්නේ හරි so therefore so the number of levels is 3 okay so then number of students in the department is 30,000 divided by 15 which is roughly 2,000 yes because there are 30,000 students and there are 15 departments. So therefore, one department will have roughly 2,000 records. Okay. Right, 2,000 records. Now remember, this is for the department ID. Okay, department ID. Now we have found the department ID. Right, now we have found the department ID. Now we have to number of students, correct. Number of block access for when the secondary index is 3 plus another 2,000. Number of block access when the secondary index. Number of block access when secondary index is 3 plus 2,000. Number of students in a department is 2,000. (2003) blocks. 2003 blocks. Ahandi mukad. Question. If each of the entry blah blah blah, calculate the total number of block accesses. Sorry, total number of block accesses. And now it is 3 level means 3 access. That is fine. And our students in one department, number of students in one department is 2,000. So if number of students in one department is 2,000, why do we have to access 2,000 different blocks? That is the question for me. Anyone has idea or come up with a logic for this one? Because I am also looking at this answer for the first time. Why the examiner has just add 2,000? 2,000 is the number of students in one department. So when number of students in one department is 2,000, it says we have to access 2003 blocks. Of course, accessing 2003 block is a huge thing. Okay, let's keep it open. Okay, I'm not very sure why examiner has taken like that. Okay, just keep it open. Okay, the final. So that up to this level, it's okay. But I'm not very sure what is the idea behind coming up with this answer. That is also okay. Number of students in department is 2,000. But why this? How can we come into this conclusion? Okay, let's keep it open. Okay. Right. Now we have the query optimization question. Okay. That is a logical level, query level. Right. So there's a select. So there are what is this? Student's name and student's department. Then we have the enrollment and course table as well. Where student ID equal enrollment student ID, that is one particular join student to enroll, and enrollment's course ID equal course ID. Now we are connecting to course table as well. We start from student and ended up in course as well. And then student's GPA must be 3.5 and course. So this is from student table, this is from course table, and its name must be engineering. And also there's another field in the course table, the lecturer must be Dr. Alice. Okay. Right. So those are the criteria. Okay. So we have the two joining things. That is the joining of first two table and the second one and third one. And then additional criteria, one from student, two from course, and nothing from the enrollment. Okay. Assume that lecturer is allowed to teach maximum of 5 courses. And about 0.1% of the students obtain GPA greater than 3.5. What would the above query retrieve? That question. What would the above query retrieve? Is it asking you to explain the result of the query? And why they have given these numbers? So those are my question now. I mean, it was something what maybe they're asking something later related to this, because I don't see any reason why. Maybe the examiner want you to explain what is the purpose of this query. Okay. So then you have to, I don't know, that is what I got. Okay. Maybe that is what the examiner is asking. I assume that these things will be used for part 2 and other things. Okay. Because I don't have to refer to this one to answer this. If it is just what is the purpose of this query. Okay. Then I will just say this will retrieve students who are following engineering and conducted by the lecturer called Dr. Alvis, engineering course conducted by, because this is a pattern matching, there can be some different engineering courses, but it has to be engineering course. The course name must have the part engineering, and the lecturer who is conducting this course must be Dr. Alvis. At the same time, the student must have got a GPA of greater than 3.5 as well. Okay, so that is for students GPA, not for that particular course. Okay, so that is my explanation. I assume this is asking for explain the query. Student, yeah, and those students' names and department ID is needed. Student name and their departments who have got GPA greater than 3.5 and follow courses where the name ending with engineering. Yes, name ending with engineering, right? Not name includes engineering, because anything and ending with engineering. So I was little bit not very specific that point. I just told you that it is the course name contains engineering, but more specifically, a course ending with engineering and delivered by the lecturer Dr. Alice. Right? So there are 2 marks given for that. So that is the easy question. I don't see any reason why you can't get marks for that. Now let's look at the optimization. Draw the optimized query tree. Remember, this is not the initial query tree. Some years they ask you to draw the initial query tree and then ask to show how it is optimized. But this is different. Straight away they ask, what is the optimized query tree? Okay, fine. So there are 3 tables. I told you that when you are doing the optimization, bring your sigma down. Okay, do those things as early as possible. Then you are not unnecessarily loading data, and you are not unnecessarily accessing the hard disk or disk. Then if you want, you can do your 5 in the memory, right? In the memory. And also, when you are joining, first do the joins that involve lesser number of records. And then do the joins that involve large number of records. Okay, so keep those things in mind. Right. So now let's see how are we going to do it. Right. So we have the course table. Student table is the biggest table with 30,000 records. Right. Is it 30,000 records? Yeah, 30,000, and departments there are only 15. And enrollment there will be 30,000 into 3. They have not mentioned anything about the courses, right? No, they have not mentioned about number of courses. But definitely the biggest table will be the student table. So therefore, make sure you join it last. Therefore, I will join first the course and enroll table. Course and enroll table. Course enroll based on course ID. You have to write that. So then that one I will be joining with the student table because that one has large number of records. Then I will do the file part. Right? I will retrieve only the required fields. I will ignore in the rest of the thing. But anyway, it will be in the memory. So make sure you take your sigma down. Okay, so here of course you can do your GPA greater than 3.5. Here in the course, make sure you do the sigma. Lecturer is Dr. Alvis, and course name is pattern matching with engineering, ending with engineering. Enrollment, you don't have to do anything, but here you have another thing that is GPA greater than 3.5. අන්නේම කළා මෙතනදී ඕනනම් මට 5 ටික කරලා අර අවශ්‍ය ෆීල්ඩ් එක විතර දාන්න. හරි. බලමු උත්තරය හරිද කියලා. Right, you can see student join is done later because it has the largest number of entries. So course they are doing this sigma and this sigma. හරි ඒගොල්ලෝ ෆයිට් කරලා තියෙනවා. නමුත් සාමාන්‍යයෙන් ෆයි කරන්න බෑ. මොකද ඒ ෆීල්ඩ්ස් විතරක් කරන් ඉන්න කියලා ගන්න නෑනේ. හැබැයි මෙමරි එකට ගත්තට පස්සේ පුළුවන්. Right? Once you get the now why we want to do the sigma first? We want to get down the sigma because if you have index field for these, we can only get those blocks. Otherwise, we may have to load all 30,000 records. Maybe if it is in 100 blocks, all 100 blocks to the memory. But now when we are doing something like this, if we have the index on lecturer, right, then we just have to go to the index file, usually the secondary index file, and get the block number of the lecturer Dr. Alvis, and you just get that block. Or maybe just one block or maximum maybe 2 blocks of courses having Dr. Alvis. Then you are doing this. So you remember again, you can't do both at the file level because file level, unless it is a composite index, either you use this index or that index. You can't use both the index because once you use an index and load it, now it is in the memory. Once the records are in the memory, how can you use a data file index? So therefore, when we say something like this, maybe for here you can use the index, not maybe the down one you can use the index, but upper one is just something you do it in the memory. Okay, and remember you can't use you can't execute 2 sigma conditions. Of course you can execute, but first you have to do one by accessing files, then the second sigma you have to do it in the memory. Okay, so therefore always what we are using is this one's index. We are not, maybe you have an index for this, but we can't use it because already we have loaded the records. Once you load the records to the memory, no point or your index is useless on that field. Then in the memory, they have restricted to only course ID because we don't need anything else. And now you are accessing the enroll. Again, we are using So why, sorry, this one. So this is enroll table, okay? That is to do join. And now we have to take in data from the student, and this is we are using the sigma down, because if there is a index for GPA, we can use that GPA index, and preferably B+3 because it's a range one. So then we can use it and load only relevant records. Now we have the student records relevant greater than 3.5. Then we have the students IDs who have done engineering conducted by Dr. Alice. Okay. Now you are doing the final join, like final sigma, this side and that side, and then you are, we need only two fields, student name and department. So therefore we get rid of all the other fields, and we are doing a projection in the memory. So this one is, we can use index, and this one you can use index. Exam, okay? Right. So these things you can't use index because now in the memory. Okay. You want index is that all? Yes. You can see it took more than 1 hour to discuss it. Okay. Right. We'll take a break. After the break, we'll discuss 2019 paper. Right. Now it's 8:16. We'll start at 8:30. Okay, so let's continue with 2019 paper, okay? Right, again, we are only looking at, because we look at the transaction questions in detail. We have done all these questions, okay? And you can see it looks pretty much the same structure. Second question. First question is, I think we discussed this. Yes. Right. Consider the database represented below with respect to reputed international company. The works on relation keeps track of which employee is working on which project. That means employee working for many projects. Project has many employees, the connecting table. Okay. Each relation has its keys underlined. So employee table is there. The project table is there. The connecting table is there. Okay. So many to many is mapped as to one to many. Therefore, I'm not going to draw that. Suppose that employee file has 30,000 records. So employee file has 30,000 records. Just mark somewhere so that you don't miss it. 30,000 records with block factor of 10. Block factor of 10. So that means 10 records per block. That means huge record size. There are 150 distinct department codes. Okay. But department table is not shown here, but they say 150 distinct department code values. It is assumed that all the employees are evenly distributed among the departments. Okay, right. There are 100 projects. So here the number of records, that means 100. And number of records is 100. So this is number is 150. This is number is 30,000. Okay. Many employees may work for any of the project, and hence assume that there may be about 250 employees per project. So what is that? There are about 100 projects. Many employees may not work for any of the projects. So So that means majority of the employees are not working for the project. So therefore they say, hence assume that there may be about 250 employees per project. For one project, that means for one project ID, there will be about 250 employee IDs. Right? One project ID will have roughly 250 employees. Okay, so that means since we have about how many projects? 100. Right? Since we have only 100 projects, here we are going to get about 100 into 250 records. So this one we are going to get roughly 250 into 100, that is 25000, 25,000 records. Okay, so the employee 30,000 records works on roughly 25,000 records. Here just 60 records. Okay, and additionally, though the department table is not there, there will be about 150 department codes. Okay. Right. Consider the following query. Select e-name, e-salary, employee name and salary, and designation, all three from the employee table. That is very easy actually. Just the employee table, no join. Right? Where department code equals sales. So usually the examiner will try to give you some marks first, right? So that you can reach to your passing marks, right? So this is that question actually. Then he will challenge you and ask, can you get into B or B plus or A plus if you are good enough, right? Suppose a multi-level index, okay? So that is this level, then this level, maybe another level, something like that level index, okay? So the examiner says, so that means usually you have large number of records and usually it is a secondary index, okay? Suppose a multi-level index on non-key attribute department code. That is why they have given you about the department code. On employee file is to be created and each entry is 16 byte long. Each record, okay? Index entry. With block size 512 bytes. Calculate the total number of block access required to perform the query above if clustered multi-level index on department code is to be used. Clustered, that is your data file is having the index and the data file is sorted by the department code rather than the primary key. Okay, let's first look at that. Okay. So clustered multi-level index. That means I thought it is an easier question, but it is also fairly a challenging question now, right? I thought they are just asking about the number of records. No. Right. So it's employee okay, clustered multi-level index. So how many records will be there on the employee? 30,000. 30,000 and block factor is 10. Okay. So employee 30,000 record and block factor is 10. BFR is 10. 10 records per block. And the block size is 512. And block size is 512 and each this is for the master table, okay, block factor. Now this is for the index entry. And index entry has the clustering field and the block pointer. 16 byte long. 16 byte long with block size of 512. 512 mana? Block size block factor. Yeah, block size is 512. block size, one block size is 512. Right. And now you can calculate the block factor, right? BFR. Block factor is number of records per block in the index file, clustering index file. 512 divided by 16. I'm using calculator. "32 blocks are needed." So 32 records per block. Right? 32. So 32. Yes, 32. "32 records per block." 32 records per block means how many blocks are needed? Number of blocks. So you have 32 blocks, 32 records per block, right? 32 records per block, and block size is 512. And number of entries is going to be 30,000. So the number of entries is going to be again, no, is it 30,000? Yes, right? Because we need one for each, right? Clustering multi-level index. This is not unique. No, right? You don't need for one department code, we can have only one block, one entry, because then in the master file, those department code are in the same. So therefore, we can just have one first record only, right? We can have for first record only. Record physical cluster field. So therefore, let's see how many departments are there. 150. So that means 150 records are needed. Right? 150 records are needed because we can just have one block, sorry, one record, one department, one record in the index file. So therefore, number of blocks needed is, we have 150 records and one block can have 32. 150 divided by 32. 4.68 means we need 5 blocks. Block 5ක් ඕන වෙනවා වැඩේ කරන්න. හරි. දැන් multi level වලට යන්න හදනවා. Block 5 block is not a big value. නේද? දැන් අර fan out එකත් එක්ක කර එක වෙනකන් යන්න ඕන. අපි ඉස්සර බලමු මෙතන නම් හරිද කියලා 5 blocks එන්නේ කියලා. Right, 32 entries per block, correct. Clustering index, number of first level blocks is 5 blocks. 5 blocks. Then අපි බලන්න ඕන fan out property use කරලා නේද? Fan out property use කරලා ඊළඟ level එකට block කීයක් වෙනවද කියලා. නේද? ඊළඟ level එකට කීයක් වෙනවද? දැන් පහ බෙදන්න ඕන මොකද block fact එකේ. මේක බෙදන්න ඕන මෙයාගේ. හරි මතකනේ? මෙයා බෙදන්න ඕන මෙයාගේ. So 5 divided by 32 is point something නේද? So therefore one block, and that means we are done. So once you get into one block, you don't have to go to another block. So therefore it will be a 2-level index, right? So 2-level index. So therefore we just have 2 level, because if it is more than 1 only, we have to go for another level. Okay, another level. So number of block access required. අන්න අර උතනින් පස්සේ එක තාවට ගිය පාර ප්‍රශ්නයක් වුණේ නේද? AR 500ද කොහෙද එකතු කරේ ආපහු? එච්චරයි කියලා දෙන්නේ. 2 level index එකක් කියලා කිව්වා එච්චරයි. So that means 2 level clustering index means you have 2 access and 1 more access to because now you get the block pointer of the master file. So that means three accesses. Sorry. මොකද මටත් තියෙන ප්‍රශ්න කලින් එකේ තව 500ක් කොහෙද එකතු කරපු එක ගැන. So 3 හැබැයි මේක කියලා නැහැ how many access කියලා. So the examiner has just find the number of levels and stop. He is not actually answering the question, right? Number of block access required. So my answer is you need 3 blocks. First level, second level, and the pointer is there now. You go and access your data file. So my answer is 3 block access. Examiner has not mentioned how many block access is needed, but he has just found that 2 block levels and he has just stopped it. Right, that is for clustering index. Okay. Now secondary index on department code is to be used. This is a separate question. Right. Secondary index on department code. So separate table now. So that means your main table is not sorted by department code. Maybe they are having the primary index that is sorted by your employee ID. Okay, employee ID. Now we are going to have a secondary index. So now you can't say one entry per one department because this is not sorted by department. මොනවද වෙනස තියෙන්නේ? දැන් කලින් අපි මෙතන කිව්වා එක රෙකෝඩ් එකයි දාන්න කියලා අපි රෙකෝඩ්ස් දාන්න 150යි කියලා. මොකද department 150 තියෙනවා. But now we are going to have how many? 30,000 entries in our index file, secondary index file. We are going to have 30,000 entries. Okay, right. Again, the block size is 512. Let's assume again the 16 byte long. එකක් 16 byte කියලා හිතමු. අරකම තමයි එකම entry එකේ නේද? block point එකයි index entry එක නේද? ඒක වෙනසක් වෙන්න බෑ. 16 byte 16 byte 30,000. Now, how many one block can have 512 bytes? One block can have 512. Therefore, what is the block factor? Now, new block factor. 512 divided by 16. Again, that is the same as the old block factor. You can have 32 entries. But number of blocks, now it's different. Number of block is one block can have 32, but now we are going to have 30,000 entries divided by 32. 30,000 divided by 32. Right. So 938 blocks are needed. 938 blocks are needed because this is a secondary index. You can't just have one record per entry per department, right? Because now departments are mixed here and there. Because most probably the primary index is there, the data file is on primary key. And now we have 938 blocks. So therefore, it's always good to go for secondary, the multi-level now. So the ඊළඟට බලන්න කොහොමද 938 බෙදන්න ඕන block factor එකේ 32. එතකොට එනවා ඊළඟ එක. ඒක ආයෙ බෙදන්න ඕන 32 වලින් එහෙම බෙදාගෙන යනවා එක වෙනකම්. ඉස්සර බලමු 938 වෙනකම් හරියද කියලා. Yes, right then. එතනත් පරද්දලා තියෙනවා 938 බෙදන්න ඕන block factor එකේ. හරි. Block factor is 32. So then that value again you are divided by 32. If it is bigger, right? Because it's not more, it's bigger than 1. So this divided by 30. මෙතන පොඩ වරදලා තියෙනවා 938 වෙන්න ඕන. So then 30 divided by 32 is 1. Now you stop and we have three level index because it's a multi-level. Okay. 3-level index. So therefore, the examiner has just stopped saying that 3-level index, but in reality, thank you. So earlier, when මෙතන තමයි ප්‍රශ්නේ දියුනේ. මෙන්න මෙතන තමයි ප්‍රශ්නේ දියුනේ. මේවට පේනවා ඇති block access through secondary index 3, that is 3 level plus 200 කියන. කොහෙන්ද 200 ආව කියලා බලන්න මට ඇත්තටම මතක නැහැ 200 කියලා ඉන්නේ ඇයි කියලා. බලන්න ඔයගොල්ලෝ ඒ කාඩ් හරි මතක තියෙන කෙනෙක් ඉන්නවනම් කියන්න. ඇයි මේ ආයි 200 access කරන්නේ? log 2 maybe yes. So then නෑ නේද අපි කෙලින්ම කියනවානේ entry එක. log 2 කතාවක් නෑ. අපි calculate කරලා 200. Number of records per depth code. Number of records per department code is 200. Number of blocks per depth code is 20 blocks. So there are 20 blocks on the 20 එකතු කරනවා. මෙතන number of records on the 200 එකතු කරනවා. Yes, number of employees, but why we are at it now? Now let's look at the secondary index. Now we know that in the third level, first level, second level, third level, now you know the block pointer, right? Block pointer, but that block pointer is because this is department code. Number of records per department code. Number of records per department code. 30,000 divided by 150, correct? There are 200 records for one department. Then why we have to add 3 plus 200? Why do we have to access another 200 blocks? Right, I think one department, one block. So once you have the block pointer, that block pointer is for the department. Right? That block pointer is for the that block pointer is for the department. Because we have 30,000. Is 2 level and this is number of blocks because that is pointing to blocks. This is pointing to entries. Right, so let's just keep it open, right? But පොඩ්ඩක් මම පුළුවන් වුණොත් ඔක ඔළුවට ඒ බොහෝ විට හෙට වෙත්තියා. මට චුට්ටක් එතන out of touch සහ මට කපාට ඔළුවට එන්නේ ඇයි කියලා. Maybe I will be able to explain it by tomorrow class. Okay. And if you find the reason, just put up it in the WhatsApp so that I don't have to think. But up to that level, until that point, we should be able to understand perfectly. Okay. Right. So we will keep it the final step open. Okay. Right. Now this is query optimization question. Consider the following query. Suppose that there are about 5 projects funded by JICA and about 10% of the employees are earning more than 2,50,000. So about 10% belong to this particular condition. And only about 5 projects funded by JICA. So that means only small number of projects here. Only 5 projects. But employee record, just give me 1 minute. Right, sorry. In employee table, there are 30,000 records, right? Yeah, 30,000 records. So 10% of 30,000 means about 3,000 records belong to this. About 3,000 records will fall into this, whereas only 5 records will be there. Only 5 records, but here 3,000 records. Okay. So therefore, it's always good to do, anyway, there's only these two, and then the join, just one join, right? So this is, now all 3 tables are used. Employee, no, 2 joins are there. Employee and work for and project. Then you have the employee side and the project side. Okay, project side. Right. They are straight away ask you to draw the optimized query tree, not the general tree. In early days, they first ask you to draw the normal query tree and then ask you to draw the optimized. But here, just optimized. Right. So we have to take the sigma down. Which join we want to do first? Okay, we'll keep this join later. Employee part. Okay, because employee table has 30,000 and still this one will take still 3,000. So therefore, let's join the project and works on. Because here you can do sigma project ID equal JICA, which will effectively give you only 5 records. And we can use the index if there is index for the funded organization. And then here we have the works on. Then to that we'll join the, to that we will join the employee. And again, without taking all the employees, make sure that you take sigma salary greater than 250,000. So then you do all the 5. Here also, if possible, if needed, you can do some 5 here because you don't need unnecessary details about the project and works on. Right? So therefore, here also you can do the 5. Then here you can do the final only required things, that is employee name and employee designation, because the employee table has some other fields as well. You can get rid of those. Here also there's another set of 5 you can do. Here you can do 5. Here you can do 5 after sigma. Here also after joining you can do some 5. Okay, so that is my one. Right? You can see the employee table. They are taken later. First, they are joining the project and work zone, but make a fine name sigma right? So this must be sigma definitely, because it will further filter it. Then you are doing set of 5, right? Here there's no sigma, you just have to do the 5 in the memory. Then you join, project ID equal project ID with the table table. So then you are doing further 5 selection projection because you don't need other fields. And here you are doing the sigma again because you can use index if they are. You don't have to take all the records to the memory. Then you just take relevant records to the memory and less disk access and less memory is needed. Then you are doing your final join. The table with the table and join and this one is definitely employee, and you are doing the final 5 and get the relevant fields on. Okay, so that kind of questions now you should be okay, and make sure the records having lesser result, not the records in the table, because you can always use your sigma and get only relevant record from the table to the memory if you have index file. So therefore, make sure the small tables you join first, then join the result you join to the table with less bigger number of records. And again, make sure that your sigma is going down, and then and there you can do your 5, right? So when you do the 5, you have to make sure that if it is in the output, you have to keep it. If it is needed in a join above, you have to keep that, right? For example, here we use employee ID. So therefore, when you file, you have to keep, sorry, here we use, employee ID. Remember the project table has the employee ID. So therefore, you have to keep employee ID because you need it for the join. Ultimately, all the fields are from the employee, but you have to keep the employee ID. Otherwise, you can't do the join. So likewise, you have to think about, right, seriously. Right, any questions? Hope this is now sort of a perfectly understood. Right? Perfectly. Right, write down the corresponding relational algebra expression for the query tree that you have produced in B1 above. So that is very easy thing, right? So here you have the sigma and then 5. Here just the 5, then you do the inner join. And then here you have another 5. And then here you have sigma and 5 and do the join, and finally you have to do another 5. So so sigma karla 5 karana. First you do the sigma, then you do the 5. Other side you just have to do the 5, no sigma, just the 5. Then those two you have to join, inner join, right? Inner join. R1, so you can give them R some names because don't use the table name. Now you have that. Then from the other side, from the employee table, you do the sigma and then 5. Then those two you have to join it again. And make sure you do the 5 also. Join kalla 5 karanna. Right? And that is your final result. So that is something you learn in your semester 2, right? Database subjects, right? I think for you guys, the database subject was in semester 1. We discussed the relational algebraic expressions. Right. Still not the end of the question. Based upon the optimal query tree produced in B1, determine the indexing mechanisms of the table, suggesting index-only plans where necessary. So index-only plans means if you just need few fields, maybe the usual index file has the index field and the block pointer. Right? So then you have to go to the master table, master file to get the other fields. Say you need just the, say you have index file employee ID. Your master employee table has employee ID, email, department ID, salary, blah, blah, blah. But your query needs only employee ID and salary. So then while your master file is having other fields, your index file, you can have both, say, employee ID, salary, and block point. Of course, you must have the block pointer, because if you need more than salary, you have to go through the block pointer to the master file. But your requirement is just the employee ID and salary. So you can get that, you already have it in the index file itself. So then you don't have to go to the master file using the block pointer. So that is what is known as index only query. So you make little more, maybe just one or two fields to the index file, so that you don't have to go for the master file to access it. But that is something, if you feel like that query is very frequently used, you do that. Otherwise, you are wasting your resources, right? Duplicating the field also. Right. Now the question is, table suggesting the index only plan where necessary, right? So for this query, right? For this query, right? So we can have, for the project table, it's not a big thing because there are only few projects. But anyway, you can suggest an index, right? For the funded organization. Funded organization. Since you just concentrate on this particular query, and it is for a specific field value, therefore even hash index is okay. Right? Hash index is okay for the project. Hash index on funded organization. Okay. For this one, you don't need an index, right? Because you are not doing any sigma. So therefore, the normal primary index you can use, right? The normal primary index, that is the project ID. Okay. Sorry. Works on has the composite primary key, right? The project ID was an employee ID. Now here range query. So therefore, for salary, we can have a B plus index because it's a range query. It's not a something like this where hash index is going to work. For this kind of things, B plus P is better. B plus P is better. Yeah, that's it, right? Do you need any other index? Of course, the foreign keys are going to have index separately. Let's see the answer. B plus so hash index on composite attribute. Oh, composite attribute. Then hari B plus 3 on index on salary. Why is that composite? Project funded organization. That is, they ask you to check the possibility of index only plan, right? I forget about that. Index only plan then it's better to go for, because we have the funded organization, right? Funded organization. So, but you have to join it using project ID, right? So therefore, we can go for multi-field index, so that we don't have to go to the data file, the funded organization and the project ID, both. Because the examiner specifically say try to use index only plans, okay? So index only plan unknown. Other table. So I got the index only plan so you can go for index only plan if you have both works on and works on and project ID and employee ID tunama තියෙන්න ඕනේ වෙයි. Yeah, because we need project ID for the join, the initial join, and employee ID for the final join. So therefore, it must be the project ID, employee ID combination. Right? Project ID, employee ID combination as a key. Maybe hash index is good enough, but composite index. Okay. Project ID, employee ID, so that we can go for another index only plan. But for final one, it's not index only plan because we have to take the name, designation, like 2 fields we need, and of course the employee ID to join. So therefore, better not to go for index only plan, because then you need 3 fields, not just 2 fields. Right. So still not the end of the story. You can see still it's the question going, right? Don't worry, because the distributed database question take only small time. Stored procedures and trigger, definitely just 5 minutes, right? Distributed database, just 5 minutes, 5 to 10 minutes. So then you have about 1.5 hours, more than 1.5 hours for the transaction and this one. Of course, transaction question also take at least half an hour, but you can take about 1 hour and do this. Okay. So you have to make sure that you do your time management. Assume that the following query is frequently used, right? Frequently used to find the project ID relevant to any given employee name. Project ID relevant to any employee name. When you give the name, they want to find the project ID. Right? So this is complicated query. They use exist also. Right? So ultimately you need the project ID. So you are taking the project ID from the works on table, but they are checking whether select all from employee where employee ID equal works on employee ID and employee name is Kasundas. So that means from the employee table, you are taking the name must be Kasundas and why are we connecting this? The name must be Kasundas. We need both employee details and but this is on the employee table, right? Because that W is already defined here. Okay, so this is a join actually. Employee table is joined with works on table. And employee table is joined with works on table, but now we are getting both employee details and the works on details, right? The details from the employee table as well as fields from the works on table. Okay. Then select project ID. So that means you are taking the project IDs where Kasundas is working. If Kasundas has worked on that particular project, right, all the project IDs where Kasundas has worked. So that is the idea behind that. Okay. Again, exist rewrite the query to improve the performance. It's unnecessarily complicated, and performance issues will also be there. Rewrite the query to improve the performance. Briefly write explain how the rewritten query will improve the performance. It is necessary to write indexing for the query. It is not necessary to write index. Index on narrow query liwa method. Phone එක ඊටදී ලේසියෙන් කරන්න. So you can just do a join, right? Just like this join. Right? So anyway, that is already in the works on table, right? Already the join has done because you need only two tables, the works on table and the project, the employee table. Select w.project ID from employee comma works on W. This is from where employee ID works on employee ID and employee name equal Kasunda. Become join inner join. It looks like that is good enough, right? We don't have to write like this. Yes, just a normal join, because just a normal join is going to work, right? So our query is correct, right? So rather than going for axis, we just do a normal inner join. Right? Inner join means if it is both belonging to both only, that record will be there. And additionally, while we are doing the inner join, we are doing additional constraint as well, filtering. Right, now that is correct because the inner join is going to work here. Right, you don't have to explain about indexes, right? So that means that's it. Yeah, that's it. Then why they are explaining? Do you have to explain it? How? Briefly explain how the rewritten query will improve the performance. You don't have to write the indexes, but you have to explain why. Right. So why? Now we can, if there's a index on name, but they are saying you don't have to, not necessary to write indexing for the query, but I think the explanation need the indexing. Okay. So we can get from the employee table, we can get the employees whose name is Kasundas. That will give you only one record, right? Typically. If you have an index on employee name, we can use it also. Then we get only one record. Then we can join, because now we got the employee ID that we works on. Right? And and if you have index there, again we can use it because we have the employee ID. And now we can just project the project ID because we will be getting all the fields from the works on table as well as the employee table. Now we can project on the necessary things. Okay, let's see the explanation. In correlated subqueries, inner query cannot be evaluated independently of the outer query because the inner subquery uses, that is the previous one. Right? So this, because this is not a join. This is inner query and outer query. So therefore, first you have to execute the inner query. Right? So then you have to join that with the outer query's P. So therefore, you can't optimize it. Right? You can't optimize it. But when you do an inner join or the normal join, but here also, if you want, you can take on the records related to customer as only, right? all the record related to custom dice. So here also we can take all the records related to custom dice and then do the join. Here you take all the records related to custom dice. I don't know the main why this is better than this. Here also we take all the records related to custom dice. Here also we have to do that. Then you join it. Here also we have to join it, right? Okay, let's see, read the explanation, because the explanation is I don't see any reason why. In correlated subqueries, inner query cannot be evaluated independently of the outer query because the inner subquery uses the values of the parent statement. That is, the inner subquery is performed for each row in the outer query. That means earlier the first thing is to run the outer query. Inner query cannot be evaluated independently of the outer query because the inner subquery uses values of the parent statement. Because inner one is using yarn, right? Right. For example, this W is in the parent statement. So therefore, inner query cannot be evaluated independently. Yes, inner query cannot be evaluated independently because even this W is from the outer query. Because works on is from the outer query. This is the inner subquery is performed for each row in the outer query. That is, the results of the subsequent subquery are dependent upon the row which is being evaluated with respect to the parent statement. Making the query uncorrelated and unnested will enable the query optimization to decide upon the best possible plan without getting constrained to explain separation of inner and outer queries. Right. Now, when you do it in as a join like this, so you can just execute the inner query first. So there's nothing called inner query. This join first. Join first. No, first you have to do this custom dash stuff, right? But then you can do the join. It's just one query. I think that there's only small performance thing. But here first you have to implement this. While you are implementing this, you are referring to the outer query. So the examiner says, therefore it is performance-wise not good. Because you are looking at both the inner query and outer query. But here there's nothing called inner query and outer query. It's just one query. Right? You just apply this filtration, then do the join, and you are done. I think this is less complicated for human user as well as for execution, because your database management system is first analyzing your SQL statement and it do something called query plan. And then it executes the query plan. That is how it's done. So therefore, I think for this one, the DBMS can generate much efficient query plan. Right? Because it's only referring to one query, not two queries, like nested queries. Okay. Is that all? Yes. Okay. Right. So that question, if you have any other, I will have a look at especially this one. Okay. Why we are adding this particular number? So that is the only doubt I'm having. Why we are adding here the number of blocks and here number of records. Okay. Number of records. I will double check and let you know that. Okay. We are having another class Friday, that is your regular class. Okay. So there we will be discussing the distributed database. Okay. Distributed database. Right. So I ask you to comment if you are planning to do middleware architecture, because middleware architecture is a very technical subject which has enterprise Java beans and blah blah blah. Of course, I can do it, but I don't know whether it's going to be worth at doing it very last moment as well. Therefore, just let me know if you feel like it's worth doing it, because anyway, if you pass e-business, you don't have to worry about the enterprise. And I know that more than 90% or 95% of the students do the e-business subject rather than enterprise application. Okay. Anyway, if you feel like you want to do it, just let me know. Otherwise, I will just keep that optional subject. Okay, because it's very technical subject as well, and it takes a lot of time because I have to explain a lot of things there. Okay, right. So we'll stop at this point. Right. Thank you.